Thank you to the organizers for giving me an opportunity to talk here in the workshop again. I'll be talking about sample preparation for electron crystallography. Please interrupt and ask something if you have a question as far as the time allows. This is an overview of my talk. There are two important methods for sample preparation techniques in electron crystallography. One is negative staining, which is basic and very established, something you know very well. Most of you are familiar with it. The second one is cryo-EM sample preparation, aiming at higher resolution. There are two important developments in cryo-EM sample preparation. One is preparing flat specimens and sugar embedding. And later I'll be talking about two practical sample preparation techniques, which is back injection method and carbon sandwich method. Negative staining is usually used for at the beginning of the structural study. It involves embedding a specimen in a layer of heavy metal salts such as granular acetate, phosphotungstic acid, and ammonium molybdate, which gives high contrast for imaging in the electron microscope. The picture I'm showing here and I will be showing here are stained with granular acetate. This is something I don't have to mention, but briefly, the procedure is very quick and easy. Briefly, 2.5 sample solution is adsorbed to a carbon-coated grid, which made hydrophilic in advance by a glow discharge, and then brought the grid with filter paper. If needed, wash with several drops of water, stain with 2 drops of negative stain, then brought the grid with filter paper and completely dry. Then the grid is ready for the electron microscopy. Negative staining is almost used for the screening of crystallization conditions, which gives the information of the morphology and quality of the specimen. The specimen is examined for the presence of vesicles, sheets, tubes, and aggregates. In good condition, the crystalline arrays can be detected, as shown here. You can see the arrays on the vesicles. Also, negative staining are also used to be crystallographic study at 2 to 3 nanometer resolution. At this low resolution, it's possible to roughly estimate the molecular surface, molecular shape, and the packing arrangement. But the disadvantages of the negative staining are staining and drying results in distortions of the molecules, and that incomplete stain embedding gives artifacts. So next, in cryo-electron microscopy, specimens are unstained, so they are nearly in a native environment and nearly artifact-free. But the contrast is very low. But the information of negative staining of the same specimen, such as crystal shape, the lattice localization, size of crystals, they help when taking cryo-EM data. For example, some crystals, good crystals are rectangular, and roundish one is not so good, poorly ordered. That's the information you can get from the negative staining. So in the cryo-EM data collection, you can skip roundish ones, and but only try to get a shot at rectangular ones. So the information of negative staining is really informative and useful for cryo-EM data collection. And crystallographic study at a middle resolution to an atomic resolution can be achieved in cryo-EM. Here it lists the proteins solved by cryo-EM at an atomic resolution or near atomic resolution. Most of these are membrane proteins. The main focus of electron crystallography is membrane proteins, because membrane proteins are embedded in lipids into the crystals, restoring the native environment. But some types of soluble proteins also amenable, also analyzed, such as alpha beta tubulin and bacterial flagella filament. Most of these were solved by using 2D crystals, and I'll be talking about mainly sample preparation for 2D crystals, but some proteins are solved using helical crystals. One of the biggest problems is the lack of specimen flatness. As shown here, the imperfect specimen flatness causes diffraction spots perpendicular to the tilt axis to be blurred or even disappeared. The lack of specimen flatness is caused by the roughness of the carbon support film and the wrinkling of carbon film supported by EM grit when the temperature is lowered to liquid nitrogen temperature or liquid helium temperature, which is called cryocrinkling. This is because of different shrinkage of EM grit and carbon film. In 1993, it has been shown that the cryocrinkling can be reduced, significantly reduced by using molybdenum grits rather than copper grits, because the thermal expansion coefficient is similar to that of carbon. So using molybdenum grits has become common. These are magnified pictures of molybdenum grits. Right one is a grit in common use, features rough surface, rough hole edges, which causes wrinkling of carbon films. In our laboratory, we are using special molybdenum grits available from Geol, which is carefully manufactured to get smooth surface, especially around the hole edges, which prevents carbon films from wrinkling. This grid has circular holes, 100 micrometer in diameter, large enough to take tilted data, because the visible area gets smaller when the grid is tilted. Using molybdenum grids is important, but also preparing flat carbon support film is very important because the crystals are adsorbed to carbon film, so anatomically flat surface of carbon support film preserve the 2D crystals, a planarity of the 2D crystals. So I will show you how to prepare high quality carbon film by vacuum evaporation. We are using pure carbon in order to prepare flat carbon film, which is set in the vacuum evaporator here. I'd like to stress here that it's very important to evaporate carbon without any spark from the rods. So in order to achieve this, we evacuated jar for more than 1 day before evaporation. Pre-evaporation technique is also needed. We sharpen one end of the carbon rod to about 1.5 millimeter in diameter and 7 millimeter long. Then the carbon is evaporated without setting marker plates until a carbon cloud is formed on the tip of the carbon rod. This is believed to be effective to prevent the sparkling. And just after this pre-evaporation, the freshly cleaved microplates are set beneath the carbonate here in the evaporator. Before setting microplates, we make sure that the surface is very smooth without serious cracks. Then the carbon is carefully evaporated and deposited onto the microplates to a thickness of 5 to 10 nanometer. The vacuum should be kept at better than 2 by 10 to the minus 6 torr. So these are blown-ups of carbon film floated onto water. Red one is sparkless carbon film, features very smooth and flat surface. Sparkless carbon film is mechanically stable, so it makes easier the sample preparation. It's easier to handle in sample preparation. Right one is the bad one, affected by sparkling. As you see, they are badly dented and more fragile. You can easily check the cracks or dents by the naked eyes when you shine on the carbon film floated onto water. So nice looking part, for example, here is picked up with a grit. One other disadvantage is that the specimen has to be studied in vacuum in the electron microscope, which could cause the dehydration of the specimen, leading to the flattening and collapse of the protein structure, because biological specimen consists of more than 80% water. One way to reduce the effect of dehydration is sugar embedding, which was introduced in 1975 when Army and Henderson published a pioneering work on structure of bacteriolopsin, in which they used glucose for an embedding medium. In sugar embedding, water surrounding a specimen is replaced by a less volatile sugar, which mimics the native environment. So far, 3 different media have been used. Glucose is used for bacteriolopsin. For LC2, tannic acid is used. Tannic acid is a glucose derivative which has a lot of phenol groups, so it's weakly acidic. So there, it is neutralized before use. And for alpha-beta tubulin, tannic acid was also used in combination with glucose. For other proteins were solved using trehalose, which is one of the saccharides consisting of 2 glucose molecules. Trehalose is synthesized in fungi, plants, and invertebrate animals, and implicated of them to survive long periods of desiccation or dehydration. So it seems reasonable to use it for an embedding medium. Sugar embedding is important in that sugar molecules fill in the crevice and grooves within proteins, preventing the flattening and collapse. The hydration is essential in the integrity of protein structure. Sugar molecules are substituted for water molecules on the protein structure and form interactions with proteins as well as lipids, as well as the head groups of lipids to preserve a native hydrated state. Also, it's known that trehalose prevents ice crystal formation, but forms vitreous state similar to amorphous ice. So what we see here is back injection method, how to prepare sugar embedded specimens. this is animation, but you can see the real sample preparation in the practical maybe tomorrow or the day after tomorrow. Also, you can check the video on the internet that one Henning nicely edited. So first, a piece of carbon film is floated onto water. This is picked up with a molybdenum crate. Then the water is replaced by embedding medium, for example, trial solution. Or otherwise, you can, in the first place, you can float carbon film onto embedding medium in buffer solution. Then the grid is turned over, and a few microliter of crystal solution is injected into carbon-free side of the grid, which is backside, and mixed. And incubate for a while to wait for crystal to adhere to be precipitated and adhere to the carbon film. Then the grid is put onto the filter paper with the carbon side up so that excess liquid is blotted off. Then the grid is picked up and air dried. Then finally quickly frozen with liquid nitrogen, plunging it into the liquid nitrogen. That's the procedure of back injection method. The remaining problem is the beam-induced image shift. This is a phenomenon which is found when you take tilted images. This causes very, very low yield of good quality images. Example, the success rate of taking good images of aquaporin 4 crystals at 45 degrees is 30% for back injection method. That of bacterial adoption at more than 60%, 60 degrees is only several percent. That of proton potassium ATPase, which is Abe-san in Fujiyoshi's lab in Kyoto University is working on, which is 5% at 20 degrees and 0 at more than 45 degrees. So collecting good tilted images is really time consuming. This is just the comparison of Fourier transforms aquaporin 4 crystals at 45 degree tilt with and without beam-induced image shift. In the case of good one, this line shows tilt axis. The spots perpendicular to the tilt axis are visible, as well as along the tilt axis. In the case of bad one, in the case of the one affected by beam-induced image shift, the spots along the tilt axis are visible, whereas the spots perpendicular to the tilt axis disappeared. Yeah. To overcome this severe problem, the carbon sandwich method was developed, in which the specimen is symmetrically sandwiched between two carbon films. This technique has proven to increase the success rate of taking good quality tilted images. The success rate of taking good images of aquaporin 4 crystals at 45 degree tilt is 90%. That of bacterial adopsin at more than 60 degree tilt increased to 90%. The success rate of proton potassium ATPase, I haven't heard that, but at least images up to 70 degree tilt has been collected. So next, I'll show you the carbon sandwich method. The procedure is part way the same as the back injection method. carbon film is floated onto water, and this is picked up with a grid. Then the water is replaced by embedding medium. The grid is turned over and a few microliter of crystal solution is injected and mixed. Then the second carbon film is floated onto water and picked up with a platinum loop like this. At this time, the size of the second carbon film should be about 2 millimeter by 2 millimeter, smaller than a grid, but large enough to cover most of grid holes. This is transferred onto carbon-free side of the grid. Then the excess liquid is brought off with a filter paper carefully. Then after some time of incubation, the grid is rapidly frozen with liquid nitrogen. That's the procedure. Next, this is a typical plot showing Fourier components of good images of accomplished crystals tilted by 45 degrees. The spots with enclosed with larger squares indicate spots with higher signal to noise ratio. And to quantitatively evaluate the quality of images, the number of good quality spots was compared between them. This is the comparison of the average number of spots with high signal to noise ratio according to the resolution. Here, near tilt axis indicates the number of spots in the area in near tilt axis. Vertically indicates the spots in the area perpendicular to the tilt axis. Notice that carbon sandwich gave more good quality spots than back injection method in all the range of resolution. In total, carbon sandwich method is on average 20% increase than back injection method, especially the spots in the vertical area showed a marked increase in carbon sandwich method. That is important region for 3D structural analysis. Thus, the carbon sandwich method produces images of better quality than back injection method in spite of increased background noise due to double-layered carbon films. This is another example. These Fourier components of proton potassium ATPase 2D crystals. Only poor images could be taken with back injection method, but much better quality data images could be taken with carbon sandwich method. Only using this carbon sandwich method, data up to 70-degree tilt has been collected. Then the cryo-EM structure at 6.5 angstrom resolution could be obtained. The crystals are proven to consist of two membrane layers here. And in the 3D map here, 1, 2, 3 molecules are in the foreground, another 1, 2, 3 are in the background. And the protein has relatively large extramembranous domains, and the protein contacts are mainly mediated by the extramembranous domains. So as you imagine, this crystal is supposed to be sensitive to drying, and so in the back injection method, the specimen will be can be easily collapsed because of specimen drying. In the back injection method, proper control of ice thickness is rather difficult, especially for such thick protein crystals, so that the protein could be easily dried and easily can be easily collapsed during sample preparation. In the carbon sandwich method, the specimen is not exposed to the air, but confined between two carbon films and surrounded by the buffer solution, so that the proteins are completely kept hydrated. I believe that the carbon sandwich is effective to keep the proteins in natural form, preserving the integrity of protein structure, and it mostly shows much better quality data. But carbon sandwich is not applicable not always applicable. For this protein, connexin 26, conventional back injection method was used. This is rather difficult protein because the 3D map reveals that the crystal consists of 3 membrane layers. So proper control of ice thickness is rather difficult both in back injection method and carbon sandwich method. The protein contacts are through their extracellular domains and forming complete gap junction channels. And the 3D map reveals that the structure in the membrane 2 is a bit different from the structure of protein in membrane 1 and membrane 3. Supposedly, this is because of the specimen drying and or mechanical contact with carbon film. So I think it's believed that the protein hemichannel in the membrane 1 and membrane 3 are supposedly deformed. But the proteins in membrane 2 are protected from specimen drying and mechanical contact with carbon film. So they used, as an embedding media, they used tannic acid in combination with high concentration of trehalose, preventing specimen drying as possible. This is the last slide. Here is the parameters of sample preparation. First, the type of embedding medium and its concentration. If the specimen is sensitive to drying, it might work if you test higher concentration embedding medium. Preparation is done usually at room temperature, but if crystals deteriorate, preparation at 4 degrees may help. How to sample to spread larger number of crystals onto the carbon film? Some types of crystals tend to stack each other for some days of incubation after harvesting. In that case, thorough agitation before sampling may induce larger number of crystals on the grid. It's the case of Akamori 4, for example. Other proteins tend not to adsorb to carbon film. For example, MZS1 crystals. In that case, you can sample from the bottom of the storage tube without serious agitation, because harvested crystals will precipitate after one or 2 days of incubation. So it may result in a larger population of crystals on the grid. Alternatively, incubation after injecting a sample, for example, several minutes or 10 minutes, may induce crystals to adhere to the carbon film. The crystal solution is usually a mixture of crystals, vesicles, and aggregates. And if the vesicles and aggregates are a lot, at a significant level, purification of crystal solution on a sucrose gradient may help removing a lot of aggregates and small vesicles, utilizing the different densities. The length of blotting and air drying determines ice thickness of the specimen. This should be optimized for your specimen depending on the humidity of the room and or how tough crystals are against drying. If the air drying is too short, the specimen will become too thick to take data. The specimen is too dry, the crystals will deteriorate in general. And you have to be careful when your crystallization buffer contains high concentration of some solutes, such as salts or glycerol. They are concentrated when preparing specimens, or even precipitated, so it will be problematic. So I usually use them low concentration in embedding medium solution. Alternatively, sample preparation at 4 degrees may help because it is highly humid and evaporation is slow. The back injection is always the first choice because it's easier to handle. Carbon sandwich is effective when you take tilted data or when you are aiming at higher resolution. But for some dehydration sensitive specimens, carbon sandwich is necessary. So that's it. Thank you for your attention.
You actually dry it and then you just put it in the microscope and then cool it down in the microscope. So my understanding was if you want to freeze the grid, you actually use colors. If you don't want it to freeze the grid, you use glucose. Is this correct? Or is this
Sorry, I couldn't get the more. Once more.
If you freeze the grid, use colors. If you don't freeze the grid, use glucose. If you just dry it, put it in the microscope and cool it down in the microscope.
Usually, I don't. You mean you put it back from the EM? No.
So usually when we do back injection, we don't freeze it in nitrogen. We just dry it, put it in the microscope.
But it may be. It may be problematic because the specimen will be too dry for some type of crystals. It may work for some type of crystals, but other type of crystals usually they'll be deteriorated.
Okay, so then when you have to freeze it, you gotta use Trellos and glucose even for back injection.
Yes. I usually first choice is Trellos. I usually, but glucose may work. I think.
My understanding was just in general, if you freeze Trellos, if you don't freeze glucose, that's kind of the
Oh.
What is other people's experience?
Just try the crystal deck, unless you have something like alcohol and you find some in a fiber. That's not a
You try just to synthesis. I mean, to give the crystal some single particles. Did you make any comparisons with any of your
Single part.
just freely? I mean, normal protein hydrated testing.
Yeah.
Did you make any comparisons for any of your crystal protein hydrated tests versus?
No, I haven't experiment that. I don't know that. I have no comment about that.
So you have on one side that you can purify the crystals from the precipitate from the empty lipid vesicles. It was sucrose gradient. Do you find the crystal?
In the literature, Shatra did it and did it for the rhodopsin crystals, and it seemed worked, but it's only if you can get a lot of crystals you can check them by sucrose gradient. But usually we hesitate to do that because the crystals are variable and it's not allowed. So maybe yeah, you can do it.
There's no more questions. Just thank all our speakers.